How much do scientists know about the composition of the universe? Chemists crafted the periodic table to organize the basic building blocks of the world, atoms. But what makes up light and the nuclei of atoms? Physicists answered these questions with the Standard Model of Particle Physics, a chart of every piece of matter ever detected. But how much of the universe does this even account for? In the 1930s, observations of distant galaxies revealed that another type of matter that didn't react with light must exist, dark matter, and at the same time a mysterious force dubbed dark energy added to our list of unknowns. Today, we realize that what we used to call matter only amounts to 4% of the universe. The other 95% is unknown. These two ideas, dark energy and dark matter, revolutionized our view of the cosmos. No longer was it only the home of galaxies and intergalactic dust, but also mysterious invisible clouds of mass and a force that counteracted gravity, sending galaxies whizzing away from each other at accelerated velocities. So how do we know that dark matter exists? The first observation of the influence of dark matter was through the motions of galaxy clusters, or hordes of galaxies crammed in small areas. The velocities of each galaxy was far stronger than the total gravity present in the cluster. This meant that each galaxy should have flown away from the cluster, but the galaxies didn't fly away. Instead, dark matter, invisible to telescopes, held the galaxies together through more gravity. Other observations of individual galaxies displayed similar effects. In the solar system, the farthest planet, Neptune, travels much slower than that of Earth in its orbit. This is because the gravity pulling on the planet is much smaller than that of the inner planets. Likewise, stars on the outskirts of galaxies should move much slower than the ones in the middle. But this isn't true. In fact, the stars travel at about the same velocity no matter where in the galaxy. This is due to dark matter surrounding the galaxy. Without the effect of dark matter, these stars would fly off into the intergalactic void. But what if dark matter doesn't exist at all? Scientists developed a theory known as MOND, or Modified Newtonian Dynamics, that solves for the motion of galaxies and their stars. It tweaks a simple equation of force developed by Isaac Newton. This equation would solve for the strange extra gravity present in the universe. MOND seems like a feasible alternative to dark matter until the collisions of galaxy clusters are observed. When two large clusters ram into each other, the galaxies inside pass each other without collision because of the large spaces between them. The intergalactic gas, though, collides and is stripped from the two clusters. Without dark matter, intergalactic gas makes up most of the mass of galaxies, but for some reason most of the mass passes through the collision and remains with the galaxy cluster. This shows that something physical must make up dark matter. This occurrence has been seen over and over again and proves MOND incorrect. What are these particles, though? One theory named MACHOs, or massive compact halo objects, states that some type of normal matter makes up the dark matter. The normal matter would most likely be either brown dwarfs, which are failed stars, or black holes, but the theory in general has many gaps. First, a massive amount of these objects would need to be in space, which is highly improbable. Also, brown dwarfs give off light that can be observed through telescopes, so if there are so many of these failed stars, why can't we see them? Their position is also problematic. Dark matter surrounds galaxies and extends far off into the intergalactic void, so how did they get out there in the first place? Scientists can map out the distribution of dark matter using a concept known as gravitational lensing, but theorists are also using this lensing at smaller scales to try to prove the existence of MACHOs. Very few of these events have been recorded, though, which points to a stranger identity of dark matter. The Standard Model holds all fundamental subatomic particles ever detected, so could dark matter be on this table? To start off, let's cross off particles that interact with light, because if dark matter did indeed interact with light, we would have already seen it. Next, particles that are unstable or break down into other subatomic particles after a short amount of time must also be crossed off, because if dark matter was unstable, it would have already broken down into other particles. Lastly, let's cross off the remaining particles that interact with a strong force, or the force that holds together atomic nuclei. If dark matter interacted with a strong force, scientists would have found it decades ago because it could interact strongly with protons and neutrons. We are left with the elusive particle known as the neutrino. Could this be dark matter? Neutrinos are what scientists call hot particles because they travel close to the speed of light. This is problematic because a universe with hot dark matter would form very differently than our current universe. Neutrinos, if dark matter, would first help form huge structures early in the cosmos, but when we look back near the Big Bang, only very small galaxies were first formed. Also, later in history, the neutrino would break apart large galaxy clusters and make them less common as time goes on. Currently, though, these structures are still forming. Therefore, we need something known as cold dark matter. This means that it travels slowly compared to other particles. This would allow for the web-like structure of the universe that we see today to form. At the bridges of these dark matter webs, galaxy clusters would be formed. So what could this cold dark matter be? Unlike the neutrino, these particles would have to be massive as to account for the influx of gravity that we see today. Scientists call these particles WIMPs, or weakly interacting massive particles. These particles would be new to the Standard Model, so what would the qualities of these particles be? There are two main qualities that scientists are looking for in the particles. First, that they are weakly interacting or can easily pass through matter. Currently, millions of these particles are probably passing through you without slowing down or crashing. And second, that they are massive, meaning that they weigh a lot compared to other particles in order to account for the gravity caused by dark matter. There are various other models of particles that fit dark matter's qualities as well, including axions, but currently WIMPs seem to be the answer. So how can we detect this dark matter? Scientists have three different routes of trying to physically find the particle. The first includes particle colliders, which smash together subatomic particles in order to create heavier particles. Scientists at CERN laboratory are smashing protons at high energies and observing the outcoming particles. If the laboratory detects a certain number of particles that account to less energy than that of what was put in, then the missing energy must be a dark matter particle. Direct measurement through interaction with heavy xenon atoms is also being attempted. In vats deep underground, scientists are observing if any reactions, whether movement or light emission, are happening. This might prove that a dark matter particle hit the xenon atom. Lastly, measurements using space telescopes are observing whether any light in the cosmos might arise from dark matter interactions. Two dark matter particles may annihilate and emit light, or a dark matter particle and a normal matter particle may interact and emit light. However the particles are detected, the discovery of dark matter is prone to occur sometime in the very near future. Its discovery will revolutionize science by opening the door to a new field of study. In the meantime, look out for dark matter. It might just fly right through you.